So, hi everyone. Um, this workshop so far has mostly focused on hydrodynamics and magnetohydrodynamics skills. And my talk here is going to change the path a little bit, and I have a little bit of a different flavor here. So, what I'm going to talk about is how we work with dynamical space states when your background geometry itself is subject to evolution in time. And that happens typically in astrophysical situations where you have a very large value of mass over radius. Basically, a very compact, very dense object is present. Near that object, the space-time gets significantly curved. Right. So, for example, in general relativity, gravity is not described as a force coming from a potential. It's described as a curvature of the geometry of the space-time fabric that these objects are actually living in. So depending on how compact the object is, the more it curves the space-time. I hope you're familiar with this concept. I'm going to assume some basic knowledge of GR in this. So now, black holes are the most compact objects that we know of in nature, or black hole-like objects, at least, followed very closely by neutron stars. But even if we want to do astrophysics around these objects, that's not truly dynamical spacetimes. That is simply curved spacetime. You can have a curved spacetime which is not evolving. Like a very common example is a supermassive black hole with an accretion disk around. Now, because the accretion disk has mass that is 10 to the power 6 times smaller than the mass of the black hole, the effect of the gas in the accretion disk is minimal to the space-time geometry. So you're not always in need of evolving Einstein's equations as a dynamical entity. Right? So you can work with a stationary curve background. Where you do need a truly dynamical gravity is when, say, you have two black holes that are interacting and coming closer to each other, for example, or two neutron stars or a neutron star and a black hole. Or maybe a star is very close to a black hole and it's depleting very rapidly with the black hole. Point. That is where you need to treat gravity as a dynamical entity. Right? I hope everyone is understanding. So the kind of system I am going to focus in this talk will be a binary system of black holes because it's the most extreme system that we can have, and that makes it all the most fun. Right? So these body systems typically they evolve in circular orbits, and they lose energy in the form of waves of space-time curvature. These are outward propagating waves. These are gravitational waves, and because they're losing energy, the black holes keep shrinking, their orbit keep shrinking until the point comes when the two black holes actually merge and a common horizon is formed. Right? So at the first time this common horizon is formed, it's a very distorted entity. And soon thereafter, it radiates away all of its homogeneities and becomes a simple curved black hole that we are all familiar with. And numerical relativity is basically the study of this entire non-equilibrium process, the entire physics that is happening from this system to the end state here. Okay, so gravitational waves are real. We have seen them, right? And these are some of the signals that we have seen over the past years. And right now, I think we have a catalog of about 100 detections already. And this figure only shows about 10 of them, right? And so these are typically the shape of the waves that are visible. Detectors on Earth. Okay, so I hope I have impressed upon you that doing numerical simulations of these dynamical binary black hole systems is necessary. In fact, there are no good semi-analytic methods that can describe these systems. Only fully numerical simulations are capable of doing so, especially close to the merger of these parts. And that is why we need numerical prediction. So here is a quick advertising figure that I show everyone. So this is a measurement, an actual measurement of a black hole's mass in multiples of the mass of our sun and its own angular momentum in some dimensionless units. And if we use information from numerical relativity, we measure these quantities as precisely as the black hole to. While if we use only perturbative methods to sort of decipher the system using gravitational wave data, the dashed measurements is what we have. And you can see the error bars are significantly higher, which means any downstream science we want to do. We want to do population science, how many black holes are there, what is the property, what is the physical nature of their formation and growth and so on, will suffer from all these giant error bars, right? So the point is, it's not just an intellectual curiosity, it's actually relevant to some kind of astrophysical systems. Okay, so this particular two-body problem, people have been trying to solve it numerically since as early as 1964, when Susan Hahn and Richard Lindquist at IBM, they tried to do an evolution of Einstein's equations, which of course did not succeed at that time. And the problem that they hit us, I will talk about it later in the show. And that problem remained unsolved for pretty much 40 years. It took 4 decades for the field to mature and produce the first stable evolutions of binary black hole spacetimes. Right? So 1964, 2004, it's almost exactly 40 years. So what are we doing here? So what are we doing here? We're trying to solve Einstein's equations that are sourced with by a matter stress energy tensor on the right hand side. This matter typically we treat it as a fluid with or without magnetic fields, and I'm not going to talk about the right hand side in this talk much because many speakers in this workshop have already spoken. I'm going to talk about how this term is actually going to feed back into the curvature. This is a specific expression for the curvature of spacetime. How this changes because this stress energy tensor is changing, right? And vice versa. So it goes both ways. And right. So I hope you're familiar with the notation and the tensors involved here. This is the Einstein tensor, Ricci tensor, the trace of it, Ricci scalar, and the matter stress energy tensor. You can write it for a fluid like this, where this is stress mass density, internal energy, pressure, and so on. So this is a deceptive equation, by the way. This is a very simple looking, very cute looking equation which doesn't really tell you how difficult it is to solve. In reality, however, there's actually 6 second order, highly nonlinear and strongly coupled equations that are hyperbolic partial differential equations, plus 4 second order, again, strongly coupled and highly nonlinear elliptic partial differential equations. There's about 10 second order equations that you have to solve in parallel all the time. It's not, So we always take for item. That depends on the kind of system. That's a problem-specific TMU. So for binary black holes, this will be mostly zero everywhere. When only at the center of the black hole is TMU not zero. Everywhere else is zero. For stars, we will approximate them as a spherical fluid ball, and it will have a density hanging on the Einstein's relationship in that star. And outside the star, again, TMU will be zero. If there are magnetic fields, then outside the star also TMU will have non-zero. Okay, so now let's start with the conceptual foundation. So in this talk, I'm going to focus mostly on sort of unraveling how we build up this procedure instead of showing the results. So we start with general relativity, and we know that it says that the world is actually full 4-dimensional space-time, and we are 3D entities. So we experience the 4D space-time, one instant of time over the next, and so on. So how do we, what I'm trying to say is space and time is treated on equal footing in GR. So how can we evolve something when there's no concept of evolution as such? Right? So there's no concept of the flowing of time necessarily in GR. Of course, we'll not have the increase of entropy in the universe because that's pretty much what brings the arrow for this. But there is a successful recipe for doing such solutions, and we have to regress back a little bit and go back to a 3 plus 1 dimension picture, where we formally split space-time into 3 plus 1 dimensions, and we treat these separately. So the first step in solving Einstein's equations is to figure out an arrow of time or invent an arrow of time. You are free to invent whatever arrow of time you want, as long as your time-like direction is always like. In the sense, what I mean is, in the 4D, you define a time field, and slices of constant time coordinate are your spatial 3D spaces. And you go ahead or backward in time coordinate, right? And along this field of time, between any 2 points, the distance must be space-like. Sorry, time-like. It should never become space-like. That's what I meant by line code. That's pretty much the only requirement you have on defining arrow of time. So now here I've shown a 3D slice, and the next 3D slice, next meaning a dt later. And this is sort of the arrow of time as it is flowing from one instant to another. So having defined this time coordinate field T, we define a normal one form. And we can also define a normal vector along that same field, such that it's a unit vector, of course. And we can define a spatial metric. So again, some notation that I've used here. Psi AB is 4-dimensional. So psi AB is the full 4D metric. And these n's are normals that are pointing outward in the time direction from each slice. So this will have a whole field of normals. This will also have its own field of normals and so on. So if you combine this in some form, you get the metric, the 3D metric in this spatial slice alone. So this governs the geometry. It tells you how to calculate distances in this 3D slice. It will have no contribution. It will not be able to tell you anything about distances perpendicular to this slice and so on. So having defined that, so we freely define an arrow of time. We can again, between one time slice to another time slice, we can redefine our spatial coordinates. So because coordinates are arbitrary, right? We are allowed to play around with it. Typically, we use that freedom to our advantage. You typically want to choose coordinates that move with your system in order to minimize the dynamics of the coordinates in that system. I mean, it's the way you can understand it. Just imagine if you're trying to evolve a sine wave that is moving straight, right? Suppose you had we had defined your coordinates in such that x is equal, some x coordinate is actually given by sine of omega t. So in those coordinates, your sine there will just be a constant. And you have absorbed the dynamics of your system in the definition of your coordinates. So that's the clever thing. These are some of the clever things that you have to do to sort of help solve more complicated problems in as less time as possible. The goal. We don't want to take 3 years to solve these things. Okay, so having redefined the spatial chart, this vector, so basically the green vector here is connecting points with the same spatial coordinates. If a coordinate observer was sitting here, they would be transported to this point. But if a stationary observer was sitting here, they would be transported to this point. Right? So this beta mu is entirely arbitrary. It can be superluminous because it's entirely of our making. In fact, in many of our simulations, we can have the spatial coordinates moving at 10 times the speed of light. And it doesn't really matter. Okay. So some again keywords. This alpha multiplying this normal vector. This is a unit normal. So alpha is what measures how much proper time has elapsed. N is only giving the direction. And beta is called the shift vector, which means, how the coordinates have shifted from one slice to the next. Okay. So now, the first was splitting space-time into space and time. The second step will be, we want to decompose any and all tensors that we have in full 4D into these spatial tensors and their time-like components. So that will be our second step. Actually, second step is figuring out how to do it. And to do, basically what we need are projection operators that will project tensors into the 3D slice and orthogonal to the 3D slice. So it turns out that the spatial metric that we have acts as a spatial projection operator, which is not a very big surprise. And you can use the unit normal, to define a n-like projection. Right? The first n is going to contract the tensor into the time direction, the other n gives it defined. So it's I hope self-explanatory. Will go up into of course auto and but that. Then now having figured that out, we can project out some of the basic quantities that we will need. So for example, any general tensor's covariant derivative that we write in this form, the full 4D covariant derivative can be projected into its 3D version using one projection operator for each index. So there's one projection operator operating on each index of this entire tensor. Right? So that is pretty much how you project any arbitrarily high rank tensors and or low rank tensors, depending on Christoffel symbols again can be written in terms of the spatial metric. These are all 3D Christoffel symbols. So unless otherwise noted, I'm talking about 3D quantities now, so spatial quantities. And you can define the Riemann tensor again using these Christoffel symbols, and so on and so forth. Okay. So now the information that is present in the full 4D Riemann tensor, so the Riemann tensor pretty much contains all the information you need to know. When you project it into a spatial slice, you do lose out on some information. What information is this? This is the information that is telling you how your spatial slice is embedded in a 4-dimensional spacetime. How it is curved in as seen from a 4-dimensional observer's point of view. And this extra information is contained in a different tensor called the extrinsic curvature of that spatial slice. It's the extrinsic curvature of spatial slice. Right? And so you can see this is the most intuitive definition. You can have other expressions for it, but this one helps me build the most intuition. So what it is doing is it is taking the covariant derivative of the normal vector to your spatial slice. Right? So it's trying to see how your normal vector is changing from one point to the other. With the twist that this is a unit normal. So it doesn't change in amplitude. It only changes in direction. So this is literally going to measure how the direction of your unit normal is changing from one point to the other on your slice. And then you project that onto using this projection of this. So this is sort of what extrinsic curvature. And I hope you get some sort of a physical feeling for this tensor as we go along. This can also be written as the Lie derivative of the spatial metric along the same unit normal. And we can go into more depth of what Lie derivatives are later if you're interested. Okay, but so 3D Ricci tensor and extrinsic curvature. These are our fundamental curvature tensors. Now, between them we have all the information. That's because we did a split of space into space, time into space. The third step is now actually applying the second step to Einstein's equations. Right? So we start with this Einstein tensor here, Einstein's equation here, and there are a few, actually exactly 3, very useful identities that come from various projections of the 4-dimensional Riemann tensor. That I'm just flashing on this slide. You don't have to remember the exact equations. All you have to remember is that they exist and what they are connecting with each other. So, for example, the first relation was derived by Kudazi, and what they do here is they project all 4 indices of the 4-dimensional Riemann into your spatial slice, all 4 indices. And what you get is that this turns out to be related to entirely 3-dimensional tensors. So there's a relation between full 4D Riemann and 3D Riemann and extrinsic curvature. So this sort of concretizes my previous statement in this slide. This information that was missing is not just contained here, it's contained in this tensor. Now, if you take other type of projections, you project once along the hand direction and then 3 times along the spatial direction, you get other relations with same things. Except because now there's a one projection along the 2 direction, you get derivatives of these extrinsic curvature. Right? So, first equation, no derivative. Second equation, first derivative. And third equation, when you do 2 time-like projections and 2 spatial projections, here, to this, right, we get the second derivative terms and so on. So, these are 3 very useful equations that we'll use in the next few slides. And then, of course, we have to take the same projections of the right-hand side of the equation, right? The Einstein equation has G and T. So, similar projections, some useful projections are you get rest mass density if you project twice along that, the momentum density or the flow of mass, basically, rate of flow of mass. If you project once along the normal and once along the spatial direction. So now, when we apply this projection to Einstein's equations, what we find is that these equations actually split into two groups of equations. Now, before explaining what those are, let's take a quick segue here. Right? And this is very basic formalism of Maxwell's equations. We studied, I don't know, class 1 or something, right? So, you see, there are two sets of equations here. And at that time, you may not appreciate it. I certainly did not. But this set is only telling us information about how electromagnetic fields right now are related to each other and themselves. They don't tell us anything about how electric fields will be or were in the past. They are instantaneous equations in some sense. That's a wrong word to use. They are more like they only define the constraints on these fields in our current spatial space. Right? These two, however, connect these fields in the current slice to the next slice to the next slice and so on. So typically these in our language are called constraint equations. Constraint equations, they constrain, and then these are evolution equations, although they can be used to evolve things. Let's keep a nomenclature simple. So we want our constraint equations to always be, basically our constraints to always be zero. That phrase will mean that these equations are satisfied in this slice, which means you have a physical solution. If you unsatisfy this, for example, if you take the right hand side of this, if you find in a numerical evolution, this is not zero, then you have moved away from the physical solution. I mean, these are differential equations. They will do what? They will do unphysical things also. You have to bring the solution back into the physical solution space by imposing these constraints. Exactly the same happens for Einstein's equations. So let's that's the trace of the extrinsic curvature. So I'm going to talk about all four in the next slides. So there are two constraint equations, two evolution equations. Let's talk about constraint equations first. So the first of them is coming from projecting Einstein's tensor twice along the normal direction and using the Gauss identity. Remember, we related three identities here. First was all spatial projections. Second was one time three spatial, and third was two time two spatial. So the first of those identity plus this left-hand side operation on this gives this equation. So this is the first constraint equation. It is one equation, right? It's a single scalar equation, as we can see. And if we replace this with T mu, then this becomes rho, this mass density. Now we have the physical form connecting some sort of conserved quantities of curvature that depend strictly on the mass density of your system. So this is our first constraint equation. This, make no mistake, these are differential equations. There are second order derivatives inside all of them, right? But they're all spatial derivatives. And these are elliptic differential equations. So anyway, then second constraint equations comes from, again, a mixed projection of an Einstein's tensor. A mixed projection combined with the second of our three identities. The one that came from one time projection and three spatial projections. You combine this operation with that, you end up with this equation that relates, simplifies the Einstein tensor in basically terms three region, three Riemann tensor. Okay, sorry. So this is the momentum constraint. It constrains the flow of extrinsic curvature in some senses. So you can see the derivative operator is acting on useless version of this extrinsic curvature. It's relating it to the actual mass currents in your system. This, however, is not one equation. This is actually three equations, right? So there's XYZ component of your mass. So there are XYZ components of this full equation. So in total, now we have four constraint equations. Okay, let's move to the evolution equations. The first evolution equations, it turns out, comes from simply the 3 plus 1 split type. We don't even have to look at Einstein's equations to get them. Simply comes from the definition of extrinsic curvature. If you remember, we defined extrinsic curvature as the d derivative of gamma n. Right? Just if along the normal direction. So now, if you add to that, it's like if you remember this d vector, is what connects the constant time coordinate observer. So you have one spatial slice, another spatial slice, you have a normal vector. This is N. And this is your D. This is alpha. And this is beta. And these are all vectors. So this is expressing only the relationship between these three. Right? And then you can write down the linear derivative along the normal in terms of this. And you can derive very quickly that the linear derivative of gamma IB along T is related to the data. This I can see. Now simplifying this equation by adopting a particular coordinate system, like x time, comma xyz coordinate system, we end up with this form of the first dimension. It's the partial time derivative of gamma ij to this gain dependent quantity shifts covariant derivatives and the extrinsic culture. So this is purely geometry. There's no physics content in here. Well, there's no matter influence in this equation. The second equation, I'm just going to flash it. Let's not go into too much depth with this. The derivation of this can be quite lengthy, but effectively it's coming from two spatial projections of Einstein's tensor. And what we end up with is this equation, which tells you the evolution equation for the extrinsic curvature itself in terms of all other three-dimensional quantities. And the effect of matter is present here. So we split space-time into space and time. We figured out how to project tensors along these dimensions. Then we actually projected Einstein's equations around the dimensions. We found 4 constraint equations that had nothing to do with time evolution. We found 6 time evolution equations, right? Both were vector equations and so on. And the last step is actually now to make everything real. To make everything real, you have to put some skin in the game. So you choose a set of coordinates because without choosing that, you can't really do anything on a computer. So the simplest coordinate you can have is the Cartesian coordinate system. So this is the unit vectors associated with that coordinate system. And in this coordinate system, we find that a normal vector has this particular form, 1 by alpha times function, and this is the shift vector. And this is the normal one form, which has this particular one. It just comes out that way. It's very straightforward to derive. Then you can write down the full 4D spacetime metric in this form. These are all 3D quantities. Together, they form the 4D metric. Please, I seem to have changed notation. This is the same as psi A in my earlier and following slide. Shouldn't say G, should say psi. Same thing for the inverse metric and so on. This is your line element in terms of these alpha and betas. And now you can have a little bit of more intuition into what these things are. You can see gamma ij is truly the spatial metric. It's only multiplying dxi and dxj, right? And I didn't just make it up. And beta is telling us how the coordinates are shifting as we go along time. Right? And alpha is telling us how time is, between slices as we move along coordinate time, how our proper time is changing. Okay, so here's a quick summary of what we all did to get these evolution. Right? And we can maybe skip over that. Now, the story is not yet complete. If you remember, we had too many choices that we had to make arbitrarily. And the first one, of course, was choosing the time direction or choosing the last function. The second was how do we choose this shift vector? We can move our coordinates around as we want, and we are free to do so in Einstein's theory. Now, these image conditions, the combined choice of these two gives us 4 degrees of freedom, and these 4 degrees of freedom are precisely your gauge. When choosing these are the same as choosing how you are slicing space-time and how one is choosing the spatial gauge condition. And this is a very important thing to note. There's decades of research in figuring out what gauges to use and what gauges to use when and what for what angles. This can be quite a difficult or a helpful thing depending on how you see it. If you choose these gauges right in a good way, you can really simplify your problems. And if you choose them naively, your code will blow up very, very quickly. When the source will come, then we see what. So one of the common gauges that is used in analytical relativity is the harmonic gauge, right? And okay, so I'm seeing a lot of blank things from your faces. I'm assuming you're not familiar with the harmonic gauge. But let's very quickly see what that specific, very special gauge is like. So this is a reach tensor, and this is one way of representing the reach tensor. This is a general equation. I've made no approximation here. The interesting thing to note here is that second derivatives are only entering in this term and this term. They are only first derivatives here, right? Remember, you can have the square of first derivatives here because they're gammas. But that doesn't mean second derivatives. Right? So now, harmonic gauge is the clever idea of using the four gauge degrees of freedom to simply set gamma b to 0, which means you have removed all the second derivatives. And what you are left with is a quasi-linear wavelength, which is much easier to solve analytically. In fact, this gauge choice was used by Bruha and others early in 1900s to prove that Einstein's equations have unique solutions. So it's a special gauge for analytic relation, not so much for numerical. It's not a very well posed gauge for solving black hole collision problems, especially when the spacetime becomes very dynamic. And I know this because of experience. It's not understood from first principles why. But what is understood is that a variation of this gauge is very useful, where we don't set gamma to 0. Our goal is to remove the second derivatives. We don't have to set gamma to 0. We can set gamma to any function that does not have a derivative, which means the derivative of gamma will only be first derivatives. So that's called a generalized harmonic gauge, where we set gamma to some algebraic function of x, y, z, and maybe the spatial metric gamma and phi and beta, but none of their derivatives should be.
How does that help?
How does that help? It helps in absorbing some of the dynamics of your curvature into your coordinates. If you choose h in a specific way, I will tell you how to choose h.
Okay.
I told you you can choose it.
So it's not arbitrary in the sense
It's
that
absolutely.
Yeah.
There's papers and papers on how to choose edge and how to choose edge better than others. It's an active research. In fact, choosing this equation is the same as imposing four differential equations on alpha and beta. You can derive that. You can calculate this equation, which is so innocuous looking, actually translates to this mess right here. Right? Okay. Are people hopefully with me so far? Okay. So now this is the scary slide. Right? So now, other than choosing this particular gauge, one last approximation that we do when we solve, there are other groups in the world that make other approximations, conditions. What we do is we don't solve these equations in their second order form. You can take any second order partial differential equation, convert it to a first order by elevating its first derivatives as free fields. So if I say that my del I psi in all equations is now a free field, free variable, its own variable, then my second order derivative of something will just become first derivative. Right? So the cost I pay is I double the equations. I already had these many equations. Now I'm going to double the number of equations. So there's nothing free that comes. Right? This is the scary part. This is what Einstein's equations that we are actually solving looks like. So this was the first where we started with. Then you get time derivatives of phi, the time derivative and spatial derivative, free fields of the spectrum. Right? So,
like is the good that Chokolsky's group was involved?
Yes. Yes. Yeah. So what makes solving these equations difficult? I mean, other than the scariness of their expressions, what really makes them difficult to solve is that there are many length and time scales that are involved in this problem. Typically, the largest length scale is the full size of your domain, and the smallest length scale is the size of your smallest black hole. And even smaller, actually, you have oscillations in the horizon of that black hole, and that oscillations would be at least 10 times smaller than the size of the black hole. Right? So the ratio of the largest to the smallest length scale can be 1,000. Easily it can be 10,000. Now, second is we are evolving spacetimes that we have never seen before. We don't know what coordinate choices will be good for them. What coordinate choices will end up happening parallelogically. And that's a big iterative process that we have to follow to figure out what choice will work. And first principle guesses can only take you so far. Equation really loses its way when it comes to very dynamical spacetimes. Then putting black holes on a grid, of course, is a problem, right? Because black hole has an infinity at the center, and we know computers don't like it. Now, the main problem that took 40 years to solve, all of these problems had to be solved. They got all solved before this 0.4 here. This, what does that mean? So remember, 4 constraint equations, 6 evolution equations. Now we start with some initial state. We solve the evolution equations, evolve the initial state. But that does not mean a constraints remain satisfied at all the points along time. Right? In fact, what typically happened was the constraints became non-zero exponentially fast. And this kept happening and happening, and people figured out how to control. And this is actually the reason why those simulations by Susan Lahn and Richard Lindquist in 1964 failed. Because constraints pretty much blew up. And they didn't have too much dynamic range in their computers. So their computers were slower than your smartphones, but they were still trying to do this. Okay, so the problem is resolving shocks, but you have heard a lot about resolving shocks, all these slope limited things. Computational challenges are nothing to sneeze at, right? You've seen the number of equations, and we just doubled them by reducing to first order. So then the accuracy which we require to solve these equations is quite high. In fact, so this is the figure showing the cost of solving these equations as a function of coordinate plane in terms of 1,000 core hours. So typically one simulation at one resolution. So this is the black is the lowest resolution, pink is the next higher resolution. This resolution never finished, there was a problem. And then it's higher and next type. And you can see every resolution takes between 10,000 to 40,000 core hours for solving just a two-point. So what we are doing is we are using the spectral Einstein code, which is a collaboration between many institutions worldwide. The key this is for a non-spinning black hole, separated by about 10 times the radius of the black hole. So 10 radius is the separation of they are in almost one side circle. That's the initial picture. Then they evolve, and this vertical drop is when the black holes emerge.
And to set the third point, like what initial conditions?
Third point?
Yeah, we just
yeah, I'll talk about this. Just give me a few minutes.
What's the curve after the formation?
This is the curve for the post-merger black hole sort of settling down into a curve. The simulation doesn't stop. It keeps going because the exploding horizon that has formed, if you remember the very first slides, it is settling down into a curved black hole. But that's much cheaper to do because again it's a single black hole. So a lot of problems 6, 7, and 5 don't exist. It's coming down to almost zero, not exactly zero. It's just not anything on the scale. If it were a normal axis, you would see it. Okay, so we use spectral methods, and I'm not sure if you've had a lecture on spectral methods, but basically what I'm going to talk about only exactly one feature of spectral methods that is good, which is you can, so say you're evolving a field. This field could be psi xx, psi xy, psi yy, psi y, psi. All of these can be treated as separate variables. Right? So every variable you decompose in some basis. Some basis you choose. You choose a simulation cube to define a set of polynomials along 8 dimensions, and the tensor product of those polynomials is your basis. That set of those tensor products are your basis functions, right? Everybody is with me so far. Now, doing this does one great thing, which is it separates out the spatial and temporal time, which is amazing because now when computing spatial derivatives, I don't have to do one more approximation. I get it for free with infinite, basically with no reduction in accuracy at all. Because spatial derivatives of theta will act only on phi. These are basis functions. By construction, you invented them. So you know what the derivatives are. And it is new. So spectral methods help you compute derivatives exactly. And this really is important because it helps your solution to converge much faster than finite difference methods. Of course, the problem, again, nothing is true. The cost, you should ask, what is the cost? What am I losing with these? What you're losing with these methods is that the moment you form a discontinuity, shock, your entire decomposition is failed. Now you have to take this left hand side again, the value of u at various x values, time values, and redo this basis expansion. So every time you have a shock, your entire expansion is gone. So these methods are best applied to smooth problems where you know discontinuities will not form. Or what you can do is you can use them until the point you know a shock and stop there. From that point, you can take finite differencing to take over and handle the shocks and come back to spectrum. Okay. A key element in how you solve problems and how you choose your domain and the domain structures and so on. The more these shapes of your domain conform to your problem, better it is. So you need cylindrical coordinates are great when you're doing accretions. But when you have two black holes, cylindrical coordinates will bring a lot of problems with that. Cartesian coordinates are, you know, just okay for many problems. Simple problems. So this is the grid we choose for solving the black hole system. And you can see there are a set of spheres drawn around the black hole, each of them. So this is shown zoomed out here. These are the two black holes and spheres around the black holes. Then there are some domains that have these truncated conical shapes and so on. Anyway, the details of these problems is not so important, not so interesting. You'll be solving other problems. But the point is important that your domain shape should correspond to the shape of the fields in your problem. Otherwise, you'll have a difficult time converging. Okay, so let's skip over calculation of initial data and let's talk about how, if you remember, the biggest problem was constraint damping. Constraints started getting violated when we start derivation. And I'm going to explain that using a simplest of equations. So this is your Einstein's equations, right? The horrible ones. I've just removed the right-hand steps. Only the differential operators are kept here. The constraints are these, right? So this is a constraint coming from reducing a second order to first order equation. This is not so important. This is the main Einstein constraint, the set of four constraints that we had. And we want this to be zero at all times, right? Throughout the animation. But it turns out, if we try to derive the expression for del t of this c, it turns out that the right-hand side has terms proportional to c with a positive constant. What does that mean? So analytical relativists will say, great, this is good. This is telling us that if you start with an initial data which satisfies the constraints for which c is zero, LTC will always be zero. So your future solutions will always satisfy your constraints, right? So you should feel happy, except if you do numerics, you should feel terribly sad because this means, how do you solve this equation? What is the solution for this equation? C is e to the power some positive factor times time, right? So if you have the smallest numerical violation of these constraints, they will blow up exponentially. And exponential blow up is, why people don't sleep at night. Right? So this is to that. So I'm going to show you how to cure this on a scalar wave system. Okay, because it's much more easy to develop your intuition. So this is my simple, nice scalar wave equation that I'm going to rewrite in a first order form. So this also illustrates how to do this. This first equation is simply the definition. This is not an equation. I mean, it's an equation, but it's coming from the definition of phi. Phi is del t outside. And phi is del I of phi is del I of psi. So this equation gives you the evolution of psi, of pi, and of phi I. Right? Now let's look at the constraints of this. It has only one constraint, the definition constraint. This one. This cannot be absorbed into the evolution equation. It has no time. So this is now a constraint. It must remain solved at all times as you go along. Right? But if you derive the constraint evolution equation for this, it's not as bad as Einstein's equation. There's no positive Ci. There is only a zero. But it still means that if you develop numerical errors, numerical violations of constraints at any time, they're going to hang around in your domain. They're going to stay in your domain forever. And they're going to pollute your solution forever. They will never dissipate. These errors will never go away. Right? So while they may not grow exponentially, they will also not decay. So again, this is simplest step. So problems are simple. But the method of solving those problems are identical. How we solve them is by introducing this term, which will help us damp away these constraint values. So I can do this, right? I can just add this term and not change the original equation, right? Because this is supposed to be zero at all. So I've just added a zero for it. But I have changed the nature of delta C. And now it comes with a negative coefficient times C. Which means this. And this is what took 4 decades to figure out for ICTS. How exactly to insert this term? How exactly to insert products of constraints into the evolution equations is that you don't have to solve the constraint equations one after. Of course, you can ask, why don't I solve constraint equations at every time step? You can do that. But solving constraint equations takes about 20,000 more times than just evolving every time. So if you thought 20,000 CPU hours is a lot, that's 20,000 times 20,000. That's how your long evolution takes. So you're not going to give that long.
So these error codes don't do.
They never.
Oh, okay.
They never do constraint evolution. That is called constrained evolution. They never do constraint. We cannot afford to do constraint.
Yeah. Yes. So they are getting out like
Constraint violations.
equation kind of
Dissipation. You're introducing, in a way, some sort of numerical dissipation for terms that you want to decay away to zero. So these are those horrible equations again, right? So you can see that there are these red terms for constraint parameters. One of them is very obvious. This gamma naught multiplying this. If you remember, this should be zero. This is a gauge condition. This should be zero. But this term exists solely for the purpose that this remains zero. It won't become zero by magic. So these gamma naught and gamma 1, these are quite tricky. Now, after having inserted these red terms, we find that our constraints actually decay in time, dissipate in time on a controllable time scale.
Why the third?
Because, what do you mean, why?
It is why the number Ci the third.
Because then I can take the derivative of it and then it will be proportional to the definition of. So ultimately the goal is to see Ci का right hand side कहाँ से है? Where is it coming from? That is the equation you want for it. Okay. And we can talk about any of this in more detail. But anyway, constraint damping done. So how do we treat singularities? There are many ways in literature of treating singularities. What we do is we simply scoop it out from our domain. We put a small sphere around the singularity that is inside the horizon but outside the singularity. And we say that we don't put any points inside that sphere. Okay? So we are excising of singularity. Why is that sphere inside the horizon? So that there are no physical fields coming out of that. So that sphere is, in some sense, one edge of our domain. So if we had a spherical domain there, it has two boundaries now. The boundary and the inner boundary around the singularities has one
It's now a kind of cell.
Two spherical cells around each of the one. But only the internal boundaries, these don't need any boundary conditions because they're inside the horizons, and it would be terribly risky to actually impose boundary conditions because we are very close to the horizon. If we knew what to put there very well, we wouldn't need to do an art.
So if there are no points there, then how does the code travel information? For example, there's a black hole in fact. There's a gravitational wave passing through the black hole
Right.
in like a modular case. How do you compute?
No, fields can flow in. Fields will flow into that boundary and flow into that boundary basically. They can go into the singularity.
Okay.
This is still a physical system, right? So you'll follow the usual laws of black holes.
Yeah.
Fields, you'll see fields flowing in,
So you
only nothing coming out.
okay.
Right? Here. This is my horizon
Yeah.
as a function of time, and this is my excitation boundary. So you feel if you measure fields here, you'll see fields flowing in. I don't know if you've learned the concept of characteristic fields. But any field you try to measure, any propagating wave measure, you can see they're all moving inward all times. And that's actually one of the criterion for defining this. Sometimes we find some field is trying to move out, and that's when we find that our code has messed up. The excitation surface is actually intersecting the one. Then we have to go back, correct it, and redo that. Okay.
How do you deal with coordinate things then?
We choose good gauge conditions, and we have a control. Our gauge conditions are time dependent, so they evolve as a function of time in a way that there are many measures for coordinate pathologies. We try to monitor them, and every time those measures are closing into zero values, we try to move the gauge conditions away from that. There are control systems, if you remember from control theory, I guess, that are governing this. Feedback control systems. We do adaptive mesh refinement, of course, and here is a picture of the mesh density, weight density. If here is blue density, the color is also density. This is the excitation surface of the bigger black, and this is a very, very small excitation surface of a smaller black hole. And you can see the grid density has naturally been increased to very high numbers here, close to the black holes. Away from the black holes, the grid is naturally less dense. But naturally, and through a captive mesh treatment. Right? So you can do AMR in two ways in spectral methods. One is you keep the shape of your domain. If it's a sphere, let it be a sphere. You only add more points in that sphere. Or you can redraw your grid, regrid. And we have to do it all of that. And yeah, this I already talked about. There are many control systems that are in play. The one I can easily explain is one that tracks horizons. So the shape of the horizon itself can be written as some r as a function of the two angular coordinates you have, right? So you expand that in terms of spherical harmonics, and that then you effectively need to control these coefficients only. And there are control systems that are making sure that this actually tracks the true horizon for all the horizons present in your system. Could be one, could be two, could be four. Okay, so that's sort of a very quick primer as to how we are doing this. I wanted to just play a quick movie that shows the evolution of two black holes. So I'm going to try and full screen here. Oops,
I can do.
pause for a second. Oh, okay. Oh, thanks. Just for a second. So I wanted to show that the colors are different. So in the outer zone, you can see this spiral-like strands. You could see it better in the earlier frames. Those are the waves that are going out. In the inner region, the color is showing the 3D Ricci scalar. Okay? The R, capital R that we have been using in our equations. And blue means small, red means large. of course. And the two horizons here are the black holes. And this is also the plane of the orbit. You will see that the plane is changing orientation. So, okay. So the camera is now fixed. Anything that changes orientation is because the system has changed its orbital plane's orientation. Right? And the arrows here are basically the direction of the flow of time. And the size of the arrows is the lapse function. So it's telling you how fast time is going for different points. There is precession going on the orbital plane. So we're getting now closer and closer to merger, and the movie is slowing down. And by the way, there's a blue curve here being drawn. This corresponds to the gravitational wave. Now this is the moment where the black holes have merged. Common horizon has. And look at how quickly it relaxed to the Earth. At the end, we have a curve. Well, now it will. Can you pause it? See this. You see this brightest pink fringes? These are the gravitational wave amplitudes merged. So they are the strongest. Pink is the strongest. And these are the earlier ones, and these are the later ones. Post-merger single black hole emission is here. And the pre-merger double black hole emission is already gone on. But the arrows represent the price. Yeah. Short, it's long. In the same amount of coordinate time, you'll fall faster when you're in this gauge choice. These are highly gauge dependent. The Ricci scalar is also gauge dependent, as well as the arrow. So the time is for an observer inside the black hole? Yes, for an observer that is sitting at the location of the arrow. So the last function is a field. It has different values at different spatial slices. This is the spatial slice. It has different values here. It has large values here. It just happens to have it in picture, but in this coordinate choice. A good coordinate system will stop it from having large values. But we didn't need a very good coordinate system for this problem because our black holes are of equal size. So this comes into second order difficulties of this. When you have very unequal mass black holes, then we need a better coordinate system that we can close to singularity, especially near the smaller holes. Okay, that's it. And
So just escape.
Escape. Okay. And this is a very quick movie. This is an old movie actually. So this is of a neutron star going around a black hole, right? And this I don't think has any magnetic fields here. It's mostly a fluid ball going inside a black hole. You can see the neutron star has been disrupted. So the neutron star was chosen in a way that it would be disrupted. We chose the equation of state of the star to be such.
So, there was another some SPH or something. How was the neutron star model?
As a fluid, as a sphere of fluid.
Okay, this all ties into another question I'll have. I'll just ask it later.
Right. So how is the neutron star modeled? If you're asking about the numerical method way, there are two separate grids acting here. There's one grid where we do spectral extractions of all your fields.
Yep.
That is on which we are evolving space-time things. There's a whole different finite difference field here, on which we evolve quantities like the density of the star, internal energy, and so on. And we are solving, yes. And then at every time, the two grids talk to each other. The space-time grid sends the space-time metric there, and that sends the T mu information there. So the two grids are highly inefficient how this does. And we are trying to improve one.
What is the density of the space-time?
I don't remember.
Like the typical.
But I mean, the density is shown here, but I don't remember what units they're in. You are talking about this star, right? Not neutron stars in general.
It's very
Don't trust. Neutron stars can. So neutron stars can be disrupted if they have if they are sufficiently large. If they have stiff enough equation of state, then they're for the same amount of mass, they are bigger. When they are bigger, different edges of the neutron star experience a large enough amount. If you take a very soft equation of state, the star becomes more compact. More compact stars don't disrupt. This simulation was done with the express purpose of disrupting the star. Can I go back into the full screen mode somehow? Sorry, slide change. How much time do you have? I'm already out. Yeah, about. Okay. So some quick results of our simulations. 2015 first gravitational wave discovery happened. This is our simulation in the discovery paper. This is data, and this is a simulation exactly lining up with data, which is great validation of years of work. Open source catalog that we released in 2016. More simulations around 2000 and 2019. Some very long simulations were performed. These took upwards of around 200,000 core hours per resolution, for example. Again, in 2019-ish. No, this is 2015 still, yeah. So this is a measure of how accurate these simulations are. Typically, they are accurate at 1% level. It's a very mainstream, I think 0.5 kilogram per the top. We have already seen this, how much they cost. They typically, for about a 20 format simulation, typically cost just 20,000 CQR, and you can scale it up highly conveniently. Now, the last point I wanted to make is that, if you remember, these were the set of difficulties. These are the difficulties that we have solved with spec. We have, of course, solved all of them, otherwise these simulations would not have been possible, but not being perfect so descriptive. We just don't do shocks very well. As I described, there's a separate grid for fluid definition, separate grid for space simulation. That's really just inefficient, right? So this is a unresolved issue. It's an unresolved issue. You can always make it more accurate for finite time, and we don't handle time scales well. There are different time scales. So basically, these are our remaining challenges that we need to solve in modern times, in contemporary times. If you're looking for doing research in this area, these are the questions that you'll be working. So what we are currently doing is we are developing a successor to spec called spec. The name is not important. What is important is that there are 3 new paradigms that we are using. And these are really very crucial things that are changing, the very fundamental things that we are changing. First is that we want to take a discretization scheme that is, if you want to calculate it, high order accuracy. You should not need information from very far away. That is what is meant by local high order. Because if you need information from very far away, then you need too much communication work. And you get bogged down by the amount of communication you keep on needing it. So this is a problem that is solved by spectral methods, right? But not by finite difference methods. B is a problem that is not solved by spectral methods and is solved by finite difference methods, right? And C is, both of them do a reasonable job. So we need a new discretization scheme that can solve all of them together. Then we need a parallelization scheme that can work for highly heterogeneous problems. If you remember, this is our domain. All the activity is happening here. Everything is happening here. Not much, just waves moving out. We are still putting a lot of so how we parallelize it is on a domain by domain basis. So one core is solving equations here, one core is solving equations here, one core is solving equations here, one here and one here, and so on. So basically, these cores that are responsible for these areas, they finish their jobs very quickly, like very eager students. And then these are the slowest cores, and everybody keeps waiting on them forever and ever and ever, and they just waste a lot of compute time if we parallelize by domain. And this is thinking like physicists. We need to think like computer scientists. That's the second problem. And the third problem is local time stepping. It's quite related. And Bhargav already touched on the CFL condition. why it is 17. So the size of your time steps depends on the smallest cell field and the fastest characteristics. Basically, the time steps needs to be small near here, but we are taking equally small time steps everywhere. Again, a waste of time, waste of computing, right? So the first problem we solved by choosing a new scheme, new meaning it was came up in 1990s, if I remember right, called discontinuous Galerkin methods, where what happens is your domain is split into subdomains as before, but now the subdomains are much smaller subdomains, not these big global spheres and so on. They're more like cube simulations, divisions of your domain. In each subdomain, you get the benefit of spectral expansion inside the subdomain. And all you need is nearest neighbor communication. And you can have approximate information flow from here to here. You don't require an exact continuity of your solutions, which means you can have shocks. You can handle shocks, movement uniform shocks. You can track the shape of the shock, and you can put these domain boundaries at the shock. So one side of the domain is on one side of the discontinuity and the other is on this side, and that will still work using teaching methods. So as compared to other methods, they have all four green arrows, right? So finite volume methods are not local at high order. If you want to do say 8th order derivative, you need 8 elements information about that side, and that's just going to slow you down fast. Spectral methods, I already said you can't do that. Finite difference methods do a reasonable job of everything except, they still require a lot of communication. Okay? So computation goes as the volume of your domain, while communication goes as the surface area of your domain. Right? Okay. Finally, local time stepping, you can do local time stepping with shorter time steps near the smaller black hole, slightly longer time steps near the bigger black hole, and much longer time steps away from the bigger black hole. It's not as easy as I've made it sound. We can discuss this in detail after my talk. Also, again, parallelization scheme. If we use MPI everywhere using a domain-based separation, we end up with a ton of waiting time, right? Remember, I showed you this is blue is when they're calculating, red is when they are just waiting. So task 2 is the slowest. It's typically solving for Einstein's equations at steps here. And all the other tasks are just waiting, which is, poor use of time. So there is some paradigm for parallelization called task-based, where all the calculations in the full domain are treated on an equal footing. The calculations are called, each atomic calculation is called a task. And these can be very, very small calculations. In term ko you can make a task. And then you throw these thousands of tasks into a common pool. And this common pool gets executed on different cores as and when the cores become free. So pretty much there is no wait time at all. We started thinking like computer scientists, not like physicists. We don't need to divide the problem by spatial. The way we are seeing the system. Okay, so with these improvements, and this is really my last slide. So our code is now able to do reasonably simple problems at least in a very scalable manner. So this one shows the accuracy as a function of the degree of spectral expansion in each element. Remember, each method, small elements, many elements. Each element has spectral expansion. So this is with only a 4th order polynomial, you get you can see the L1 error in fields. And this is actually the real figure that I show and advertise, which you can see because of task-based calculus, it scales just out of the box. You will take the code onto a supercomputer which has about 500,000 cores, and it scales linearly. You can't scale more than linear. That's impossible. So linear is the best you want. And so typically our old codes would do this, the green curve. They will plateau after some number of cores, and at this point communication dominates. So you throw more CPUs, doesn't matter, communication dominates. So this is sort of a future-proof way of doing expensive codes. It doesn't need to be used for scalar arrays or simpler. By simpler, I don't mean conceptually simpler, I mean computationally. So that's it. Spectre is open source. Just go on GitHub. Just Google Spectre #. You'll find it. And with this, I rest. I'm already. Any questions? You now later.